The Internals of Postgres. Chapter 5, Concurrency Control. Concurrency control is a mechanism that maintains consistency and isolation, which are two properties of the ACID when several transactions run concurrently in the database. There are three broad concurrency control techniques, i.e. multi-version concurrency control, MVCC, strict two-phase locking, S2PL, and optimistic concurrency control, OCC. And each technique has many variations. In multi-version concurrency control, each write operation creates a new version of a data item while retaining the old version. When a transaction reads a data item, the system selects one of the versions to ensure isolation of the individual transaction. The main advantage of multi-version concurrency control is that readers don't block writers, and writers don't block readers. In contrast, for example, a strict two-phase locking based system must block readers when a writer writes an item because the writer acquires an exclusive lock for the item. Postgres and some relational database management systems use a variation of multi-version concurrency control called snapshot isolation, or SI. To implement snapshot isolation, some relational database management systems, e.g. Oracle, use rollback segments. When writing a new data item, the old version of the item is written to the rollback segment, and subsequently the new item is overwritten to the data area. Postgres uses a simpler method. A new data item is inserted directly into the relevant table page. When reading items, Postgres selects the appropriate version of an item in response to an individual transaction by applying visibility check rules. Snapshot isolation does not allow the three anomalies defined in the ANSI SQL 92 standard, i.e. dirty reads, non-repeatable reads, and phantom reads. However, snapshot isolation cannot achieve true serializability because it allows serialization anomalies, such as write skew and read-only transaction skew. Note that the ANSI SQL 92 standard based on the classical serializability definition is not equivalent to the definition in modern theory. To deal with this issue, serializable snapshot isolation, SSI, has been added as of version 9.1. Serializable snapshot isolation can detect the serialization anomalies and can resolve the conflicts caused by such anomalies. Thus, Postgres version 9.1 and later provide a true serializable isolation level. In addition, SQL Server also uses serializable snapshot isolation. Oracle still uses only snapshot isolation. This chapter comprises the following 4 parts. Part 1. This section provides basic information required for understanding the subsequent parts. Describes transaction IDs and tuple structure, and how tuples are inserted, deleted, and updated. Part 2 describes the commit log, clog, which holds all transaction states, transaction snapshots, and the visibility rule check rules. Part 3 describes the concurrency control in Postgres using specific examples. Section 5.7 describes the visibility check. This section also shows how the three anomalies defined in the ANSI SQL standard are prevented. Section 5.8 describes preventing lost updates, and Section 5.9 briefly describes serializable snapshot isolation. Part 4. This part describes several maintenance processes required to permanently run the concurrency control mechanism. The maintenance processes are performed by vacuum processing, which is described in Chapter 6. This chapter focuses on topics that are unique to Postgres, although there are many concurrency control related topics. Note that descriptions of deadlock prevention and lock modes are omitted. Transaction isolation level in Postgres. Postgres implemented transaction isolation levels are described in the following table. Isolation level, dirty reads, non-repeatable read, phantom read, serialization anomaly. So we have the read committed isolation level, that dirty reads are not possible, non-repeatable read is possible, phantom read is possible, and serialization anomaly is possible. Isolation level, repeatable read, dirty reads not possible, non-repeatable read not possible, phantom read not possible in PG, possible in ANSI SQL, serialization anomaly possible, isolation level serializable, dirty reads are not possible, non-repeatable read is not possible, phantom read is not possible, and serialization anomaly is not possible. Postgres uses serializable snapshot isolation for data manipulation language, e.g. select, update, insert, delete, and 2PL for data definition language, e.g. create table, etc. 5.1 Transaction ID. Whenever a transaction begins, a unique identifier, referred to as a transaction ID, TXID, is assigned by the transaction manager. Postgres's TXID is a 32-bit unsigned integer, approximately 4.2 billion. If you execute the built-in TXID current function after transaction starts, the function returns the current TXID as follows. So begin, and then select TXID current, and you'll get the current transaction ID. Postgres reserves the following three special TXIDs. 0 means invalid TXID, 1 means bootstrap transaction ID, which is only used in the initialization of the database cluster. 2 means frozen transaction ID. Transaction IDs are compared with each other. For example, at the viewpoint of the transaction ID 100, transaction IDs which are greater than 100 are in the future, and they are invisible from the transaction ID 100. Transaction IDs which are less than 100 are in the past and visible. Figure 5.1, Transaction IDs in Postgres. So we have the past and the future, visible, invisible. Transaction identifier space as a circle. Past, future. It's the rollover of the 32-bit unsigned so don't have over 4.2 billion transactions at once. Seems safe. Since the transaction ID space is insufficient in practical systems, Postgres treats the transaction ID space as a circle. The previous 2.1 billion transaction IDs are in the past, and the next 2.1 billion transaction IDs are in the future. Note that the so-called transaction ID wraparound problem is described below. Note that the begin command does not assign a transaction ID. In Postgres, when the first command is executed after a begin command executed, a transaction ID is assigned by the transaction manager, and then its transaction starts. 5.2 Tuple structure. Heap tuples in the table pages are classified as an unusual data tuple and a toast tuple. This section describes only the usual tuple as a usual. A heap tuple comprises three parts, i.e., the heap tuple header data structure, null bitmap, and user data. See figure 2. So we have this heap tuple header data, we have this null bitmap, and user data. The heap tuple header data structure is defined in source include access htup details.h. While the heap tuple header data structure contains 7 fields, 4 fields are required in the subsequent sections. txmin holds the transaction ID of the transaction that inserted this tuple. txmax holds the transaction ID of the transaction that deleted or updated this tuple. If this tuple has not been deleted or updated, txmax is set to 0, which means invalid. tcid holds the command ID, CID, which means how many SQL commands were executed before this command was executed within the current transaction beginning from 0. For example, assume we executed 3 insert commands within a single transaction: begin, insert, 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 commit. If the first command inserts this tuple, tcid is set to 0. If the second command inserts this, tcid is set to 1, and so on. tctid holds the tuple identifier, tid, that points to itself or a new tuple. Tid, described in section 1.3, is used to identify a tuple within a table. When this tuple is updated, the tctid of this tuple points to the new tuple. Otherwise, the tctid points to itself. 5.3 Inserting, deleting, and updating tuples. This section describes how tuples are inserted, deleted, and updated. Then, the free space map, FSM, which is used to insert and update tuples, is briefly described. To focus on tuples, page headers and line pointers are not represented in the following. Figure 5.3 shows an example of how tuples are represented. So we have the page header, then some pointers which would go to these tuples. So the tuple and it has 7 fields, but the 4 that we're focusing on are the txmin, the txmax, the tcid, the tctid, and the user data. Which the tcmin holds the transaction ID that inserted this tuple. The txmax hold the transaction ID that deleted or updated this tuple, or 0 if it hasn't been updated or deleted. And then the tcid holds the command ID starting from 0, the number of commands within this transaction. And then the tctid holds the tuple identifier that points to itself or a new tuple. (5.3.1) Insertion. With the insertion operation, a new tuple is inserted directly into a page of the target table. So begin insert into table values A. This is the transaction ID. It's not being deleted or updated, so this is 0. This is the first command within the transaction, so this is 0. And then this is the tuple identifier that points to itself or a new tuple, so it will point to the new tuple. Suppose that a tuple is inserted in a page by a transaction whose transaction ID is 99. In this case, the header fields of the inserted tuple are set as follows. Transaction xmin is set to 99 because this tuple is inserted by transaction ID 99. txmax is set to 0 because this tuple has not been deleted or updated. tcid is set to 0 because this tuple is the first tuple inserted by transaction ID 99. tctid is set to 0, 1, which points to itself because this is the latest tuple. Page inspect. Postgres provides an extension, page expect, which is a contribution module to show the contents of the database pages. Create extension page inspect. Create table data text. Insert into table values A. Then select LP as, or select one page, first page, 1p as tuple txmin, txmax, tfilled3, tfilled3 as tcid, and then tctid. From heap page items, get raw page table 0. 5.3.2 Deletion. In the deletion operation, the target tuple is deleted logically. The value of the transaction ID that executes the delete command is set to txmax of the tuple. See figure 5.5. So we have transaction ID 111. I would have thought that this would be 111 as well, because begin commit, no? Suppose that tuple 1 is deleted by transaction 111. In this case, the header fields of tuple 1 are set as follows. If transaction ID 111 is committed, tuple 1 is no longer required. Generally, unneeded tuples are referred to as dead tuples in Postgres. Dead tuples will eventually be removed from pages. Cleaning dead tuples is referred to as vacuum processing, which is described in Chapter 6. 5.3.3 Update. In the update operation, Postgres logically deletes the latest tuple and inserts a new one. Update the row twice. Suppose that the row which has been inserted by transaction ID 99 is updated twice by transaction ID 100. When the first update command is executed, tuple 1 is logically deleted by setting transaction ID 100 to the tmax, or setting txmax to 100 to transaction ID 100. So this is logically deleted. And then tuple 2 is inserted. Then the tctid of tuple 1 is rewritten to point to tuple 2. The header fields of both tuple 1 and tuple 2 are as follows. Tuple 1, txmax is set to 100, and the tctid is rewritten from 01 to 02. And tuple 2, txmin is set to 100, txmax is set to 100, or txmax is set to 0, tcid is set to 0, tctid is set to 02, which points to itself. When the second update command is executed, the first update command, as in the first update command, tuple 2 is logically deleted and tuple 3 is inserted. The header fields of both tuple 2 and tuple 3 are as follows. Tuple 2, txmax is set to 100, tctid is rewritten to point to the next tuple from 02 to 03, and tuple 3, the txmin is set to 100, the txmax is set to 0, the tcid is set to 1 because it's the second command in the transaction, and tctid is set to point to itself, which is 03. As with the delete operation, if transaction 100 is committed, tuple 1 and tuple 2 will be dead tuples, and will be dead tuples. And if transaction ID 100 is aborted, tuple 2 and tuple 3 will be dead tuples. 5.3.4 Free space map. When inserting a heap or an index tuple, Postgres uses the free space memory of the corresponding table or index to select the page which can insert it. As mentioned in section 1.2.3, all tables and indexes have respective free space maps. Each free space map stores the information about the free space capacity of each page within the corresponding table or index file. All free space maps are stored with the suffix FSM, and they are loaded into shared memory if necessary. PG Free Space Map. The extension PG Free Space Map provides the free space of the specified table/index. The following query shows the free space ratio of each page in the specified table. Create extension PG Free Space Map. Select star, round 100 times available divided by 8 kilobytes, 2 as free space ratio from PG free space on the accounts table. Block number, available free space ratio. That's neat. 5.4 Commit log, clog. Postgres holds the statuses of transactions in the commit log, or clog. The commit log, often called the clog, is allocated to the shared memory and used throughout transaction processing. This section describes the status of transactions in Postgres, how the clog operates, and the maintenance of the clog. 5.4.1 Transaction status. Postgres defines 4 transaction states: in progress, committed, aborted, and subcommitted. The first 3 states are obvious. For example, when a transaction is in progress, its status is in progress, etc. Subcommitted is for sub-transactions, and its description is omitted from this document. 5.4.2 How clog performs. The clog comprises one or more 8 kilobyte pages in shared memory. The clog logically forms an array. The indices of the array correspond to the respective transaction IDs, and each item in the array holds the status of the corresponding transaction ID. Figure 5.7 shows the clog and how it operates. So it's clog, transaction 1, transaction 2, the state, T1, transaction ID 200 commits. The status of transaction 200 is changed from in progress to committed. Transaction and then T2, transaction 201 aborts. The status of transaction 201 is changed from in progress to aborted. When the current transaction ID advances and the clog can no longer store it, a new page is appended. When the status of a transaction is needed, the internal functions are invoked. Those functions read the clog and return the status of the requested transaction. 5.4.3 Maintenance of the clog. When Postgres shuts down, or whenever the checkpoint process runs, the data of the clog is written into files stored under the pgclog subdirectory. Note that pgclog will be renamed to pgexact in version 10. These files are named 0000, 0001, etc. The maximum file size is 256 kilobytes. For example, when the clog uses 8 pages, the first page to the 8th page, the total size is 64 kilobytes. Its data is written into 0000, 64 kilobytes, and with 37 pages, 296 kilobytes, the data are written into 0000 and 0001, whose sizes are 256 kilobytes and 40 kilobytes, respectively. When Postgres starts up, the data stored in the pgclogs files, pgexact files, is loaded to initialize the clog. The size of the clog continuously increases because a new page is appended whenever the clog is filled up. However, not all the data in the clog is necessary. Vacuum processing, described in Chapter 6, regularly removes such old data, both the clog pages and files. Details about removing the clog data is described in section 6.4. 5.5 Transaction Snapshot. A transaction snapshot is a dataset that stored information about whether all transactions are active at a certain point in time for an individual transaction. Here, an active transaction means it is in progress or is not yet started. Postgres internally defines the textual representation format of transaction snapshots as 100:100:. For example, 100:100: means transaction IDs that are less than 99 are not active, and transaction IDs that are equal to, equal, or greater than 100 are active. In the following descriptions, this convenient representation form is used. The built-in function txid current snapshot and its textual representation format. The function txid current snapshot shows a snapshot of the current transaction. Select txid current snapshot. Let me get this. The textual representation of the txid current snapshot is xmin:xmax:xip list, and the components are described as follows. xmin, the earliest transaction ID that is still active. All earlier transactions will either be committed and visible or rolled back and dead. Xmax, first as yet unassigned transaction ID. All transaction IDs greater than or equal to this are not yet started as of the time of the snapshot and thus invisible. XIP list. Active transaction IDs at the time of the snapshot. This list includes only active transaction IDs between xmin and xmax. For example, in the snapshot 100:104:100, 102, xmin is 100, xmax is 104, and the XIP list is 100 and 102. Two specific examples are shown in the following. Figure 5.8. Examples of transaction snapshot representation. 100:100. The first example is 100:100. This snapshot means the following. Transaction IDs that are less than 99 are not active because xmin is 100. Transaction IDs that are equal or greater than 100 are active because xmax is 100. The second example is 100:104:100, 102. This snapshot means the following. Transaction IDs that are equal or less than 99 are not active. Transaction IDs that are equal or greater than 104 are active. And transaction IDs 100 and 102 are active since they exist in the XIP list, whereas transactions 101 and 103 are not active. Transaction snapshots are provided by the transaction manager. In the read committed isolation level, the transaction obtains a snapshot whenever a SQL command is executed. Otherwise, in the repeatable read or serializable isolation levels, the transaction only gets a snapshot when the first SQL command is executed. The obtained transaction snapshot is used for a visibility check of tuples, which is described in section 5.1. When using the obtained snapshot for the visibility check, active transactions in the snapshot must be treated as in progress, even if they have actually been committed or aborted. This rule is important because it causes the difference in the behavior between read committed and repeatable read, or serializable. We refer to this rule repeatedly in the following sections. In the remainder of this section, the transaction manager and transactions are described using a specific scenario in figure 5.9. So we have 5 transactions. We have some select, a few selects, and commit. The transaction manager always holds information about currently running transactions. Suppose that 3 transactions start one after another, and the isolation level of transaction A and transaction B are read committed, and that of transaction C is repeatable read. Transaction 1. Transaction A starts and executes the first select command. When executing the first command, transaction A requests the transaction ID and snapshot of this moment. In this scenario, the transaction manager assigns transaction ID 200 and returns the transaction snapshot 200:200:. Transaction 2. Transaction B starts and executes the first select command. The transaction manager assigns transaction ID 201 and returns the snapshot 200:200 because transaction A, transaction 200, is still in progress. Thus, transaction A cannot be seen from transaction B because it's active. T3. Transaction 3 starts and executes the select command. The transaction manager assigns transaction ID 202 and returns the transaction snapshot 200:200:. Thus, transaction A and transaction B cannot be seen from transaction C. Time 4. Transaction A has been committed. The transaction manager removes the information about this transaction. Time 5. Transaction B and transaction C execute their respective select commands. In this scenario, transaction B requires a transaction snapshot because it is in the read committed level. In this scenario, transaction B obtains a new snapshot 201:201 because transaction A, transaction 200, is committed. Thus, transaction A is no longer invisible from transaction B. Transaction C does not require a transaction snapshot because it is in the repeatable read level and uses the obtained snapshot, i.e. 200:200:. Thus, transaction A is still invisible to transaction C. (5.6) Visibility check rules. Visibility check rules are a set of rules used to determine whether each tuple is visible or invisible using both the tx-min and tx-max of the tuple, the clog, and the obtained transaction snapshot. These rules are too complicated to explain in detail. Therefore, this document shows the minimal rules required for the subsequent descriptions. In the following, we omit the rules related to subtransactions and ignore discussion about tc-tid, i.e., we do not consider tuples that have been updated more than twice within a transaction. The number of selected rules is 10, and they can be classified into 3 cases. 5.6.1 Status of tx-min is aborted. A tuple whose tx-min status is aborted is always invisible. Rule 1. A tuple whose tx-min status is aborted is always invisible because the transaction that inserted this tuple has been aborted. This rule is explicitly expressed as the following mathematical expression. Rule 1. If status tx-min equals aborted, invisible. 5.6.2 Status of tx-min is in progress. A tuple whose tx-min status is in progress is essentially invisible, rules 3 and 4, except under one condition. If this tuple is inserted by another transaction and the status of tx-min is in progress, this tuple is obviously invisible, rule 4. If tx-min is equal to the current current transaction ID, i.e., this tuple is inserted by the current transaction, and tx-max is not invalid, not a 0, this tuple is invisible because it has been updated or deleted by the current transaction. Rule number 3. The exception condition is the case whereby this tuple is inserted by the current transaction and tx-max is invalid. In this case, this tuple is visible from the current transaction. This is rule number 2. So we have rule 2, if status of tx-min is in progress, what is this? And tx-min equals to current transaction ID. Man. I bet the author would appreciate if went through and proofread. You know? That'd be cool. I mean, he did, just give this book out for free. It's pretty neat. 5.6.3 Status of the TX min is committed. A tuple whose TX min status is committed is visible. See rules 6, 8, and 9, except under 3 conditions. Rule 6 is obvious because TX max is invalid or aborted. 3 exception conditions, and both rules 8 and 9 are described as follows. The first exception condition is that TX min is active in the obtained transaction snapshot, Rule 5. Under this condition, this tuple is invisible because TX min should be treated as in progress. The second exception condition is that TX max is the current transaction ID. Rule number 7. Under this condition, as with Rule 3, this tuple is invisible because it has been updated or deleted by this transaction itself. In contrast, if the status of TX max is in progress and TX max is not the current transaction ID, Rule 8, the tuple is visible because it has not been deleted. The third exception condition is that the status of TX max is committed and TX max is not active in the obtained transaction snapshot, Rule 10. Under this condition, this tuple is invisible because it has been updated or deleted by another transaction. In contrast, if the status of TX max is committed, but the TX max is active in the obtained transaction snapshot, Rule 9, the tuple is visible because TX max should be treated as in progress. (5.7) Visibility check. This section describes how Postgres performs a visibility check, i.e., how heap tuples of the appropriate versions in a given transaction are selected. This section also describes how Postgres prevents the anomalies defined in the ANSI SQL 92 standard: dirty reads, repeatable reads, and phantom reads. 5.7.1 Visibility check. Figure 5.10 shows a scenario to describe the visibility check. In the scenario shown in Figure 5.10, SQL commands are executed in the following time sequence. At time 1, we start the transaction to ID 200. Time 2, we start the transaction 201. Time 3, we execute select commands of both transactions. Time 4, we execute the update command of transaction ID 200. Time 5, we execute select commands of both transactions. Time 6, we commit transaction ID 200. And time 7, we execute the select command of transaction 201. To simplify the description, assume that there are only 2 transactions, i.e. transaction ID 200 and 201. The isolation level of transaction 200 is read committed, and the isolation level of transaction ID 201 is either read committed or repeatable read. We explore how select commands perform a visibility check of each tuple. Select commands at time 3. At time 3, there is only tuple 1 in the table, and it is visible by Rule 6. Thus, select commands in both transactions return Jekyll. Rule 6. The status of one and the TX max is invalid, invisible. Select commands of time 5. First, we explore the select command executed by the first transaction, that with transaction ID 200. Tuple 1 is invisible by rule 7, and tuple 2 is visible by rule 2. Thus, this select command returns hide. Time 5. Right here. But this is going to return Jekyll. Then, or no. Let's find out. Yeah, okay. Thus, the select command returns the updated hide. So now, on the other hand, in the select command executed by the second transaction, that with transaction ID 201, tuple 1 is visible by rule 8, and tuple 2 is invisible by rule 4. Thus, this select command returns Jekyll. Rule 8. Status committed. If the updated tuples are visible from other transactions before they are committed, they are referred to as dirty reads, also known as write-read conflicts. However, as shown above, dirty reads do not occur in any isolation levels at any isolation level in Postgres. Select command at time 7. So time 7, the first transaction has been committed, so this should also get the hide, right? Or no? Yeah? No? Maybe not. Where's it? In the following, the behaviors of the select commands of time 7 in both isolation levels is described. First, we explore the transaction ID 201, the second transaction. First, we explore when the second transaction is in the read committed level. So this one, in the read committed level, it's going to return not hide Jekyll, right? Oh, God damn it. Read committed level. Okay, read committed level, it says read any committed, even if the commit happened during the transaction. In this case, the first transaction, that with transaction ID 200, is treated as committed because the transaction snapshot is 201. So you get a new snapshot at each command. Yeah. Okay. New snapshot at each command, not just at the start of the transaction. So in this case, the first transaction is treated as committed because the transaction snapshot is 201:201, and anything less than that is visible and not active. Therefore, tuple 1 is invisible by rule 10, and tuple 2 is visible by rule 6, and the select command returns hide. Note that the result of the select commands, which are executed before and after the first transaction, that with transaction ID 200, is committed, differ. This is generally known as non-repeatable reads. Let's repeat that. Note that the results of the select commands, which are executed before and after the transaction is committed, differ. This is generally known as non-repeatable reads. So within the same transaction, we have non-repeatable reads because we have this, right? Either one of these, this select will be different from this last select. Even though this is within the same transaction here, this other transaction makes it change from here to here. If read committed, if repeated, repeatable read. If repeatable read, though, we don't get the, what was that? What was the anomaly? The non-repeatable read anomaly. In contrast, when the second transaction is in the repeatable read level, the first transaction must be treated as in progress because the transaction snapshot is 200:200:. You get the same snapshot for the entire transaction, it looks like. Therefore, tuple 1 is visible by rule 9 and tuple 2 is invisible by rule 5, and the select command returns Jekyll. Note that non-repeatable reads do not occur in the repeatable read and serializable level. Seems like hint bits. To obtain the status of a transaction, Postgres internally provides 3 functions. Transaction IDs is in progress, transaction ID is in progress, transaction ID did commit, and transaction ID did abort. These functions are implemented to reduce frequent access to the clog, such as caches. However, bottlenecks will occur if they are executed whenever each tuple is checked. To deal with this issue, Postgres uses hint bits, which are shown in the following. So we have heap xmin committed, heap xmin invalid, heap xmax committed, heap xmax invalid. When reading or writing a tuple, Postgres sets hint bits to the mask of the tuple if possible. For example, assume the Postgres checks the status of the txmin of a tuple and obtains the status committed. In this case, Postgres sets a hint bit heap xmin committed to the tinfo mask of the tuple. If hint bits are already set, transaction ID did commit and transaction ID did abort are no longer needed. Therefore, Postgres can efficiently check the statuses of both txmin and txmax of each tuple. Phantom reads in Postgres's repeatable read level. Repeatable read is as defined in the ANSI SQL 92 standard allows phantom reads. However, Postgres's implementation does not allow them. In principle, snapshot isolation does not allow phantom reads. Assume that 2 transactions, transaction A and B, are running concurrently. Their isolation levels are read committed and repeatable read, and their transaction IDs are 100 and 101. First, transaction A inserts a tuple. Then it is committed. The txmin of the inserted tuple is 100. Next, transaction B executes a select command. However, the tuple inserted by transaction A is invisible by rule 5. Thus, phantom reads do not occur. So if you started the transaction, 5.8, preventing lost updates. A lost update, also known as a write-write conflict, is an anomaly that occurs when concurrent transactions update the same rows, and it must be prevented in both the repeatable read and serializable levels. This section describes how Postgres prevents lost updates and shows examples. 5.8.1 Behavior of concurrent update commands. When update command is executed, the function execUpdate is internally invoked. The pseudocode of execUpdate is shown below. So for each row that will be updated by this update command, while true, if the target block is being updated, then wait for the termination of the transaction that updated the target row. If the status of the terminated transaction is committed, and the isolation level of this transaction is repeatable read or serializable, then abort this transaction. First updater win. Otherwise, go to step 2. I didn't know that there was a go-to in SQL. Wow, I'm a noob. Maybe not that we should be using it, but neat. The second block. Else if the target row has been updated by another concurrent transaction, then if the isolation level of this transaction is read committed, then update the target row. Otherwise, abort this transaction. First updater win. Third block. Else the target row is not yet modified or has been updated by a terminated transaction. Update the target row. So we have 1. Get each row that will be updated by this update command. Repeat the following process until the target row has been updated or this transaction has been aborted. 3. If the target row is being updated, proceed to step 3. Otherwise, proceed to step 8. 4. Wait for the termination of the transaction that updated the target row because Postgres uses first updater win scheme in snapshot isolation. 5. If the status of the transaction that updated the target row is committed and the isolation level of this transaction is repeatable read or serializable, proceed to step 6. Otherwise, proceed to step 7. 6. Abort this transaction to prevent lost updates. 7. Proceed to step 2 and attempt to update the target row in the next round. 8. If the target row has been updated by another concurrent transaction, proceed to step 9. Otherwise, go to 12. Step 9. If the isolation level of this transaction is read committed, proceed to step 10. Otherwise, go to step 11. 10. Update the target row. Proceed to step 1. Start over. 11. Abort this transaction to prevent lost updates. 12. Update the target row and proceed to step 1 because this target row is not yet modified or has been updated by a terminated transaction, i.e., there is a write-write conflict. This function performs update operations for each of the target rows. It has a while loop to update each row, and inside of the while loop branches to 3 blocks according to the conditions shown in the following figure. So the 3 internal blocks of execUpdate. So the first update, or the first block, is the target row is being updated. So we have a couple updates waiting. It is being updated. So wait. Updated. Aborted. Block 2. The target row has been updated by the concurrent transaction. Or 3, there is no conflict, the easy case. 1. The target row is being updated. Being updated means that the row is updated by another concurrent transaction and its transaction is not terminated. In this case, the current transaction must wait for the termination of the transaction that updated the target row because Postgres' snapshot isolation uses the first updater win scheme. For example, assume that transactions A and B run concurrently, and B attempts to update a row. However, A has updated it and is still in progress. In this case, transaction B waits for the termination of transaction A. After the transaction that updated the target row commits, the update operation of the current transaction proceeds. If the current transaction is in the read committed level, the target row will be updated. Otherwise, in the case of repeatable read or serializable isolation level, the current transaction is aborted immediately to prevent lost updates, right? Because this updated it, and then it would update again. It'd be like, oh hey, you missed this update. 2. The target row that has been updated by the concurrent transaction. The target row has been updated by the concurrent transaction. The current transaction attempts to update the target tuple. However, the other concurrent transaction has updated the target row and is already committed. In this case, if the current transaction is in the read committed level, the target row will be updated. Otherwise, the transaction is aborted immediately to prevent lost updates. And 3, there is no conflict. When there is no conflict, the current transaction can update the target row. First updater win versus first committer win. Postgres' concurrency control based on snapshot isolation uses the first updater win scheme. In contrast, as explained in the next section, Postgres' serializable snapshot isolation uses the first committer win scheme. 5.8.2 Examples. 3 examples are shown in the following. The first and second examples show behaviors when the target row is being updated, and the third example shows behavior when the target row has been updated. So we have transaction A and B update the same row in the same table, and their isolation level is read committed. Transaction B is executed as follows. After executing the update command, transaction B should wait for the termination of transaction A because the target tuple is being updated by transaction A. After transaction A is committed, transaction B attempts to update the target row. In the second round of exec update, the target row is updated again by transaction B. Example 2. The same, but their isolation levels are read committed and repeatable read, respectively. The behavior of transaction B is described as follows. After executing the update command, transaction B should wait for the termination of transaction A. After transaction A is committed, transaction B is aborted to resolve conflict because the target row has been updated and the isolation level of this transaction is repeatable read. Example 3. Transaction B, repeatable read, attempts to update the target row that has been updated by the committed transaction A. In this case, transaction B is aborted. (5.9) Serializable snapshot isolation. Serializable snapshot isolation, SSI, has been embedded in snapshot isolation since version 9.1 to realize a true serializable isolation level. Since the explanation of serializable snapshot isolation is not simple, only an outline explained. In the following, the technical terms shown in below are used without definitions. Precedence graph, known as a dependency graph, and serialization graph, and serialization anomalies. Example, write skew. 5.9.1 basic strategy for serializable snapshot isolation implementation. If a cycle that is generated with some conflicts is present in the precedence graph, there will be a serialization anomaly. This is explained using the simplest anomaly, right skew. Figure 5.12.1 shows a schedule. Here, transaction A reads tuple B, and transaction B reads tuple A. Then transaction A writes tuple A, and transaction B writes tuple B. In this case, there are two read-write conflicts, and they make a cycle in the precedence graph of this schedule, as shown in figure 5.12.2. This schedule has a serialization anomaly, the right skew. Conceptually, there are three types of conflicts: write-read conflicts, which are dirty reads, write-write conflicts, like lost updates, and write-read conflicts. However, write-read and write-write conflicts do not need to be considered because, as shown in the previous sections, Postgres prevents such conflicts. Thus, serialization snapshot isolation implementation in Postgres only needs to consider read-write conflicts. Postgres takes the following strategy for the serializable snapshot isolation implementation. 1. Record all objects, tuples, pages, relations, accessed by transactions as SI read locks. Or SI read locks. Detect read-write conflicts using SI read locks whenever any heap or index tuple is written. 3. Abort the transaction if a serialization anomaly is detected by checking detected read-write conflicts. 5.9.2 Implementation of serializable snapshot isolation in Postgres. To realize the strategy described above, Postgres has implemented many functions and data structures. However, here we use only two data structures: SI read locks and read-write conflicts to describe the SSI mechanism. They are stored in shared memory. For simplicity, some important data structures, such as serializable exact, are omitted from in this document. Thus, the explanations of the functions check target for conflict out, check target for conflict in, and pre-commit check for serialization failure are also extremely simplified. For example, we indicate which functions detect conflicts. However, how the conflicts are detected is not explained in detail. If you want to know the details, refer to the source code predicate.c. SI read locks. An SI read lock, internally called a predicate lock, is a pair of an object and virtual transaction IDs that store information about who has accessed which object. Note that the description of virtual transaction ID is omitted. Transaction ID is used rather than virtual transaction ID to simplify the following explanation. SI read locks are created by the check target for conflicts out function whenever one DML command is executed in serializable mode. For example, if transaction ID 100 reads tuple 1 of the given table, an SI read lock, tuple 1, 100, is created. If another transaction ID 101, reads tuple 1, the SI read lock is updated to tuple 1, 100, 101. Note that a SI read lock is also created when an index page is read, because an index page is only read without reading the table page when the index only scans feature, which is described in section 7.2, is applied. SI read lock has three levels: tuple, page, and relation. If the SI read locks of all tuples within a single page are created, they are aggregated into a single SI read lock for that page, and all SI read logs of the associated tuples are removed, to reduce memory space. The same is true for all pages that are read. When creating an SI read log for an index, the page-level SI read log is created from the beginning. When using sequential scan, a relation-level SI read log is created from the beginning regardless of the presence of indexes and/or where clauses. Note that in certain situations, this implementation can cause false positive detections of serialization anomalies. The details are described in section 5.9.4. Read-write conflicts. A read-write conflict is a triplet of an SI read lock and two transaction IDs that reads and writes the SI read lock. The check target for conflicts in function is invoked whenever either an insert, update, or delete command is executed in serializable mode, and it creates read-write conflicts when detecting conflicts by checking SI read locks. For example, assume that transaction ID 100 reads tuple 1 and then transaction ID 101 updates tuple 1. In this case, the check target for conflicts in function invoked by the update command in transaction 101 detects a read-write conflict with tuple 1 between transaction ID 100 and 101, then creates a read-write conflict R100 write 101 tuple 1. Both check target for conflict out and check target for conflict in functions, as well as the pre-commit check for serialization failure function, which is invoked when the commit command is executed in serializable mode, check serialization anomalies using the created read-write conflicts. If they detect anomalies, only the first committed transaction is committed, and the other transactions are aborted by the first committer win scheme. 5.9. How serializable snapshot isolation performs. Here we describe how serializable snapshot isolation resolves write skew anomalies. We use a simple table shown below. Let's create this table: ID int primary key, flag boolean default false, and then we generate a series. Then we analyze the table. Transactions A and B execute the following commands. So we're creating this write skew scenario. So we start both transactions in isolation level serializable, and then we're doing a select on both and then an update on two different this is the case where this is selecting this and then we're selecting here. There. Assume that all commands use index scan. Therefore, when the commands are executed, they read both heap tuples and index pages, each of which contains the index tuple that points to the corresponding heap tuple. See figure 5.14. Relationship between the index and the table in the scenario above. Time 1. Transaction A executes a select command. This command reads a heap tuple 2000, and one page of the primary key, p key 2. Transaction B, and then time 2. Transaction B executes a select command. This command reads a heap tuple 1, and one page of the primary key, p key 1. Time 3. Transaction A executes an update command to update tuple 1. Transaction B executes an update command to tuple 2, or to tuple 2000. Transaction A commits, then transaction B commits. However, it is aborted due to a write skew anomaly. Figure 5.15 shows how Postgres detects and resolves the write SKU anomaly described in the above scenario. Time 1. When executing the select command of transaction A, check target for conflicts out creates SI read locks. In this scenario, the function creates two SI read locks, L1 and L2. L1 and L2 are associated with PK2 and tuple 2000 respectively. T2. When executing the select command of transaction B, check target for conflicts out creates two SI read locks, L3 and L4. L3 and L4 are associated with PK1 and tuple 1 respectively. T3. When executing the update command of transaction A, both check target for conflicts out and check target for conflicts in are invoked before and after exec update. In this scenario, check target for conflicts out does nothing. Check target for conflicts in creates a read-write conflict C1, which is a conflict of both PKey1 and tuple 1 between transaction B and transaction A, because both PKey1 and tuple 1 were read by transaction B and written by transaction A. T4. When executing the update command of transaction B, check target for conflicts in creates read-write conflict C2, which is the conflict of both PKey2 and tuple 2000 between transaction A and transaction B. In this scenario, C1 and C2 create a cycle in the precedence graph. Thus, transaction A and B are in a non-serializable state. However, both transactions A and B have not been committed. Therefore, check target for conflicts in does not abort transaction B. Note that this occurs because Postgres's serializable snapshot isolation implementation is based on the first committer win scheme. Time 5. When transaction A attempts to commit, pre-commit check for serialization failure is invoked. This function can detect serialization anomalies and can execute a commit action if possible. In this scenario, transaction A is committed because transaction B is still in progress. Time 6. When transaction B attempts to commit, pre-commit check for serialization failure detects a serialization anomaly and transaction A has already been committed. Thus, transaction B is aborted. In addition, if the update command is executed by transaction B after transaction A has been committed at time 5, transaction B is immediately aborted because check target for conflicts in invoked by transaction B's update command detects a serialization anomaly. If the select command is executed instead of commit at time 6, transaction B is immediately aborted because check target for conflicts out invoked by transaction B's select command detects a serialization anomaly. .9.4 False positive serialization anomalies. In serializable mode, the serializability of concurrent transactions is always fully guaranteed because false and negative serialization anomalies are never detected. However, under some circumstances, false positive anomalies can be detected. Therefore, users should keep this in mind when using serializable mode. In the following, the situations in which Postgres detects false positive anomalies are described. Figure 517 shows a scenario where false positive serialization anomaly occurs. When using sequential scan, as mentioned in the explanation of SI read locks, Postgres creates a relation-level SI read lock. Figure 18.1 shows how SI read locks and read-write conflicts shows SI read locks and read-write conflicts when Postgres uses sequential scan. In this case, read-write conflicts C1 and C2 are associated with the table's SI read lock, which are associated with the table's SI read lock are created, and they create a cycle in the precedence graph. Thus, a false positive write skew anomaly is detected, and either transaction A or B will be aborted even though there is no conflict. Even when using index scan, if both transactions A and B get the same index SI read lock, Postgres detects a false positive anomaly. Figure 519 shows the situation. Assume that the index page pkey1 contains two index items, one of which points to tuple 1 and the other points to tuple 2. When transaction A and B execute respective select and update commands, pkey1 is read and written by both transaction A and B. In this case, read-write conflicts C1 and C2, both of which are associated with pkey1, create a cycle in the precedence graph. Thus, a false positive write skew anomaly is detected. If transaction A and B get the SI read logs of different index pages, a false positive is not detected and both transactions can be committed. 5.10. Required maintenance processes. Postgres' concurrency control mechanism requires the following maintenance processes. 1. Remove dead tuples and index tuples that point to corresponding dead tuples. 2. Remove unnecessary parts of the clog. 3. Freeze old transaction IDs. 4. Update free space map and VM virtual map and the statistics vacuum map. I can't remember VM here. Not virtual machine. The need for the first and second processes has been explained in sections 5.3.2 and 5.4.3 respectively. The third process is related to the transaction ID wraparound problem, which is briefly described in the following subsection. In Postgres, vacuum processing is responsible for these processes. Vacuum processing is described in Chapter 6. 5.10.1. Freeze processing. Here, we describe the transaction ID wraparound problem. Assume that tuple 1 is inserted with transaction ID 100. That is, tx min of tuple 1 is 100. The server has been running for a very long period, and tuple 1 has not been modified. The current transaction ID is 2.1 billion plus 100, and a select command is executed. At this time, tuple 1 is visible because transaction ID 100 is in the past. Then, the same command is executed. Thus, the current transaction ID is 2.1 billion plus 101. However, tuple 1 is no longer visible because transaction ID 100 is in the future. This is the so-called transaction wraparound problem in Postgres. To deal with this problem, Postgres introduced a concept called frozen transaction ID and implemented a process called freeze. In Postgres, a frozen transaction ID, which is a special reserved transaction ID 2, is defined such that it is always older than all other transaction IDs. In other words, the frozen transaction ID is always inactive and visible. The freeze process is invoked by the vacuum process. The The freeze process scans all table files and rewrites the tx-min of tuples to the frozen transaction ID if the tx-min value is older than the current transaction ID minus the vacuum freeze min age. The default is 50 million. This is explained in more detail in Chapter 6. For example, as can be seen in Figure 521A, the current transaction ID is 50 million, and the freeze process is invoked by the vacuum command. In this case, the tx-min of both tuple 1 and tuple 2 are rewritten to 2. In version 9.4 later, the x-min frozen bit is set to the tinfo mask field of tuples rather than rewriting the tx-min of tuples to the frozen tx ID. Alright, that's all for today. Cheers.